Lastly, we're going to look at this extra problem about bounding practice. So, given an array of n elements, the heapification operation, which is taking that array and turning it into a valid max heap or min heap, but for heap sort purposes, max heap, right? The heapification operation permutes the elements of the array into a heap. There are many solutions to the heapification problem. One approach is bottom-up heapification, which treats the existing array as a heap and rearranges all nodes from the bottom up to satisfy the heap invariant. So in other words, it's calling swim up on every single node, working from the bottom to the top. Another approach is top-down heapification, which starts with an empty heap and inserts all the elements into it one at a time. And so those are some examples of different solutions. But why can we say that any solution for heapification must require at least linear time? Well, I guess a pretty straightforward or logical solution is that in order to check that an array satisfies the heap invariant, we at least have to look at every element, right? And so that takes linear time. In other words, if there are n elements in the array and we have to look at all of them at least to figure out if it satisfies our heap or heap property, then it's going to take n time. Now, moving on to part B. The worst case runtime for top-down heapification is in theta n log n. Why does this mean that the optimal solution for heapification takes big O of n log n? Take a moment and think about this one. Okay, so the worst case runtime for top-down heapification is theta n log n. Why does this mean that the optimal solution for heapification takes big O n log n time? Hopefully you've taken a moment to think about this problem, and now we're just going to sort of think about this. So we know that big O describes an upper bound on an operation, right? Or in other words, it's describing the fastest rate at which it could possibly grow with respect to the input. And we know that at least one solution, it's taking theta n log n time, right? That's the worst possible case, which means that our upper bound, the worst possible case takes this much time, which means we have a limit, or in other words, we know exactly what the worst case is, and that provides an upper bound. And so it's appropriate to say that the optimal solution has big O n log n time. Now, we have done 4a and 4b, and we want to show that the worst case runtime for top-down heapification is in theta n log n. So in other words, we're proving this statement right here. In this slide, we just took it as fact and accepted that, this is true, which leads us to having this big O n log n for top-down heapification. But now we have to prove it. And so we can take a moment and think about how to do this. And so hopefully you've paused the video and thought about this for a little bit. And let's go with a pretty intuitive, simple approach. When you are inserting elements into a heap, in the worst case, you've inserted some amount so far, and you go to add something new, and it needs to swim all the way up to the top, right? Because when we add new elements, we put them at the bottom rightmost position and then swim them up as necessary. And so this means if it has to swim all the way up to the top, it's going to be roughly log n, because that's the max height of our heap. And if we have to do this for all n elements, then that's n log n. This is a pretty high level, rough, intuitive answer. You can go a little more in depth with the math, right? Because technically when you first start, there's not all n items, it's one. And then, so you have to do a summation, basically, to add all the elements in. But to leave it a little more intuitive so that, this is something you could probably do on an exam or just within the scope of this class, we can just logic out adding to a heap in the worst case takes log n time, and we have to do this for all n elements we want to put. So that's theta n log n in the very worst case. And that was a pretty, I guess, gut instinct approach to this problem. If we want a more mathematical way of thinking about it, maybe we should think about this level by level. So in the very worst case, you insert the first element into the 0th level, or in other words, the root, and that requires, a little work, right? And then when we want to insert the second and third elements, in the worst case, let's say we insert the second element and we have to swim it up one level, and then we insert the third element and that also has to swim up one level because we're always adding things that are smaller bigger. So they're always swimming up because they belong at the top in this worst case. And then inserting elements at the second level is going to require swimming up 2 levels. And inserting elements at the third level, in the worst case, requires swimming up 3 levels. And so we're seeing that at the I level, you have to swim up roughly I levels, right, to reach the top in the worst case. That's the most work you can do. And you have to do that for every single item you insert at that level. Well, how many items are there per level? At the top, there is 1 element, and then you double that, and then you double that again, and then you double that again. So in other words, at the ith level, there are 2 to the I elements. And in the worst case, for each of those elements, you have to swim it up from the bottom to the top, because we're looking at the worst case here. So this means a total work of 2i times I for every single layer in the heap. And we know that in a heap with n elements, there are log n layers. This means that the total work done is going to be the summation. So basically for every level, we're summing up the total work. We know we start at level 0 and we go up to level log n, because that's the height of our heap. And at every level, we do 2i to the I work. Now the question is, how do we actually take this sum and then turn it into something we can work with? Again, I want to emphasize this is a little more mathy than we usually care about in 61B, but it's definitely interesting, right? And so the first thing we're going to maybe notice is that we're summing over I, and we're going from 0 to log n. And so we can do a little bit of approximation here and say, whatever this is, we know it's going to be less than or equal to if we just pull out basically summing all of the i's. And so we can say this is less than or equal to log base 2 of n, and we're keeping the same bound, 2 to the I. And now we have to figure out a way to deal with this. Again, this is another little bit of a math hack, but if we take this and we were just, going to look at some of the terms, we'd see that 2 to, when I equals 0, 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, etc. And eventually we'll get up to 2 to the log base 2 of n, because that's, the last thing we're getting to. And math hack, we know that this is in theta n. And so again, I'm not expecting anyone to really know this off the top of their heads. I'll be honest, I didn't either. But we can say that this is in theta n, which means this whole part is roughly n, and so we get n log n at the end. Log n times n. And so we've shown that the worst case runtime for top-down heapification is in theta n log n. Again, that more gut instinct approach of just like inserting a bunch of things and having to swim up or swim all the way up every time is log n. Now we have to do that for all n elements. That totally works as well. Now the last part of this problem says, show that the worst case runtime for bottom-up heapification is in theta n. And so in bottom-up heapification, we call swim down on every node from bottom to top, or in other words, like right to left in our underlying array. And so to find out the total work done in bottom-up heapification, we should just sum the total work done to swim down every node in the heap, which means we should sum the work done at every layer of the heap, or like every level, right? And so we know that the number of levels in the heap is in log n, right? The height of a heap is log n. Now, for each call to swim down, let's say we're calling swim down on this one, how much work do we have to do? Well, for things at the leaf level or the bottom of our heap, they don't have to do any work, right? And the elements here have to swim down one level, and the elements at the top have to swim down, log n levels, or like the height of the tree, right? So the root has to, in the worst case, swim all the way down to the bottom, and the elements at the leaf don't have to move at all. And so this is a key observation here. Notice that the most elements are at the leaf level, right? Which means the most elements are doing very little work because they don't have to move at all. And the place where we have to do the most work in the worst possible case, right? The root is the one who has the worst potential height to travel. Well, there's only one of them at the root. And so in comparison, it's sort of small. And so we can see how bottom-up heapification is sort of optimizing the amount of work we have to do. The things with the potential to do the worst amount of work are in very few in number, right? Whereas the things that don't have to do a lot of work, there's a lot of them. And so we're sort of minimizing in that aspect. So we know that items at the bottom are going to be doing the least work. And so let's just say we've labeled our max heap such that this is actually level 0, and this is level log n, or the root. Now our numbers work out really nicely such that we can say things at level I do I work, right? Because they have to move down I, right? If you ask a leaf to swim down, in the worst case, nothing happens, or it's 0 work. If you ask something at level 1 to swim down, in the worst case, it moves down 1 level or does 1 work. And if you ask something at the root to swim down, in the worst case, it travels the whole height of the heap, so log n. So our numbers work really well if we do this, even if it's a little intuitive, because we usually think of the root as 0, right? But this helps our numbers work out. And so that's how much work a single thing at level I does when you ask it to swim down, and how many nodes are there per level. Well, doing some math, we're going to see this works out to roughly 2 to the log n minus I minus 1, and I is the layer number. And so putting this all together, we just want to sum the amount of work done per node on a given layer. So we know that every node at a layer does 2 to the I, or 2 to the log n minus I minus 1. And there are I nodes on that layer. So the total work done is going to be the sum of this product for all layers. And what's the range of values that we need to sum over for I? Well, the layer number is going to range from I equals 0 to I equals log n. And so we sum I to log n minus I minus 1. And now we can do some math and figure out what really happened here, right? So we can first maybe pull out a couple things. And so if we do 2 to the log n, we know that's, or log base 2 of n, we know that's just n, right? And then we also have 2 to the minus I, or that's multiplied basically by 2 to the minus I minus 1, right? Because these together equal. And so we're taking this and we've expanded it. So this would simplify to n for this term, and then 2 to the I plus 1. And so we've taken those negatives and just moved 2 to the bottom. So another positive. Now, what's the next step we have to take? Well, we can actually pull out this n, right? Because summing over I, n is considered a constant here. The other thing we can do is we can actually pull out basically a 1 over 2 squared. And so in doing this, the constant we end up pulling out is n over 4. And in pulling out that 1 over 2 squared, we just have to subtract. And so we've subtracted like 2 to the 2. So, oops, this is minus 1, sorry. So we've subtracted basically 2 powers of 2. And so we end up with this. And that might seem a little bit nonsensical, but you'll see again, this helped our math work out. And so, and I just realized I wrote that I was pulling out the n and still included it. So this is what we look like right now, right? In other words, we look like this. 1/2 to the I minus 1 power. Now, for ease of calculation, let's just say x equals 1/2, so I don't have to keep writing 1/2 over and over again. So this actually just becomes x, right? And this is just helping us so we don't have to get confused by all the numbers and constants floating around, right? So we have this whole thing. And to make things a little simpler, we can definitely say that this sum is going to be less than or equal to the sum to infinity of I, x, I minus 1. And once again, another little math hack. Now that we know this, we can take it to n over 4 x and so these are things that you're just going to recognize if you have taken some higher level math classes. And we know that this sum is actually, this sum, the derivative of this sum is equivalent to 1 over 1 minus x squared. And if we go and plug back in our 1/2 again, then we will get n over 4, 1 over 1 minus 1/2 squared, which is equal to 1 over 1/2 squared, which is equal to 4, because I guess maybe I jumped the gun a little bit, but you can do the math and you'll see it works out, which means n over 4 times 4 is n. We've ended up with beta n. That was a super complicated mathematical approach. I will be honest and say that even I am not the best equipped to teach this, since I'm here as a CSTA, not a math teacher. And so I wouldn't expect anyone to fully understand how we did all the steps for this. This is not really in the scope for CS61B. But if you like seeing that mathematical explanation, then maybe that satisfied you. Essentially, the idea is just that each level is roughly doubling the work. And so the total runtime dependency on n sums up to be linear. And that is this whole worksheet. Thank you for tuning in.